Hey everyone, welcome back to another video by Camroom 5. Today's video is going to be about chemical equilibrium and the equilibrium constant in terms of concentration that we call Kc constant. For that we need strong basics of reversible reaction because we know that when an equilibrium begins, obviously the concentration of all involved substances changes. Whether they are reactants or products, their concentrations begin to change. For example, we have a reactant and a product. Initially, we have reactants in the container. So the maximum amount belongs to the reactant and product is technically 0.00 because product hasn't been produced yet. In terms of used up amounts, some amount of the reactant is used up. The product isn't used up, but the product is produced. And when we say that, at equilibrium, what happens is that left over reactant is there. Reactant was there in the beginning, now it's left over because it's been used up and some product is produced. Imagine this hypothetical equation where a mole of P reacts with 2 moles of Q to produce 2 moles of R and 3 moles of S. Initial, used up, and left over amounts. Hypothetically, let's imagine that I had 5 mole of each reactant and obviously there was no product because the product isn't produced yet. Imagine that I say in my scenario, for example, 1 mole P has been used up. Now obviously 1 mole of P reacts with 2 moles of Q. So definitely 2 mole of Q would have been used up because the ratio suggests that. In terms of left over, out of 5 mole P, 1 is reacted, so 4 mole P is left over and 3 mole Q is left over. Moving on, 1 mole of P reacts to make 2 mole of R. So if we find out how much R is produced, it should be 2 mole of R. And moving on with the ratio, 1 mole of P makes 3 mole of S. So 3 mole of S should be produced by the P that reacted. So we put in that at the equilibrium, all these reactants and products are still left. This is when the equilibrium has been established. This is present at equilibrium. We are not concerned with the amount used up, we are concerned with the amount produced. If we plot a graph of the amounts over time, we get to know that on the y-axis, if we put the moles of the P and Q, which were both 5 moles in the beginning at time 0, P and Q were 5 mole each. I'm using blue line for P and red line for Q. The amount of P drops from 5 to 4 and the amount of Q drops from 5 to 3. If we follow the amount of R and S, we can see that the amount of R started from 0 but it reached a value of 2 moles and the amount of S started from 0 moles and then we were able to achieve 3 mole S. You can see the reactants are not hitting 0. Because the reaction is at equilibrium, it reaches equilibrium at almost 7.2-ish, 3-ish minutes because you can see the concentrations are becoming constant. This means the equilibrium is established at around 7.3 minutes. The rate of forward reaction is equal to the rate of backward reaction. Now, we are concerned with a ratio of the product concentration at equilibrium divided by the reactant concentration at equilibrium, both raised to the power of their mole ratios. That is called Kc. It's a constant. Let's define Kc. Kc is defined as the ratio of the product concentration at equilibrium, not just initial or used up, at equilibrium, raised to the power of their mole ratios mole ratios we get from the equation. So raised to the power of its mole ratio over the reactant concentration at equilibrium. Again, we are concerned with the amount of reactant left. We are not concerned with the amount used up. So reactant concentration at equilibrium raised to the power of its mole ratio at a specific temperature. Kc value is dependent upon temperature. Let's write that. Kc is dependent upon temperature. Kc is a constant, but Kc changes when the temperature changes. We will also see that Kc is variable for each equation. Like for example, our hypothetical equation, Kc will have product R raised to the power square and product S raised to the power cube as numerators. Q raised to the power square and P raised to the power 1 would be denominators. The square brackets in a Kc expression suggests that we are talking about the molar concentrations. So make sure for Kc you use a square brackets. It means mole per unit decimeter cube. The powers are obtained from the mole ratios of a balanced equation, and then you also quote the temperature, XYZ temperature. Let's solve this equation. It says the experiment is repeated at another temperature. 2.50 mole of ammonium chloride. See, this is the equation over here. Let me write it back. Ammonium chloride is in equilibrium with ammonia and HCl. All are aqueous in my case, so all of these are aqueous. Were taken and at equilibrium 1.30 mole ammonium chloride is left. Complete the table. So 2.50 mole ammonium chloride was there. Ammonia and hydrogen chloride are products, so they were not present in the beginning. Obviously, if the question says 1.3 has been left, so total is equals to used per left. 2.5 was the total. I don't know how much is used up, but I do know that 1.30 is left over. So the amount used up should be equal to 1.20 mole of ammonium chloride. So I put it as 1.20 mole ammonium chloride is used up and 1.30 is left. Now the ratio suggests that 1.20 was used up and the ratio is 1:1 between ammonium chloride and ammonia. So obviously 1.20 mole ammonia should have been made. And also HCl is also 1:1 ratio. So also HCl is 1.20 made or produced in the equation. And these are all left at equilibrium. So the Kc expression will have ammonia and HCl in square brackets as the product and ammonium chloride in square bracket as a reactant. Their mole ratio is 1:1, so no powers here. I'm putting their moles, dividing by the moles of the reactant, and I'm assuming that the volume is 1 decimeter cube. So the mole is the concentration here. When I solve it on a calculator, I get to know that the answer turns out to be 1.107, but I'm rounding it off, so 1.108. What are the units for the Kc expression here? Let's find that out. You know, in Kc, the ammonia and HCl were both mole per decimeter cube, and they both were numerators. So 2 times I'm putting mole per decimeter cube, and the reactant was also mole per decimeter cube as denominator. I cancel out the units, and I get to know that the units for this Kc is going to be mole per decimeter cube. So the units of Kc are also variable based on the equation. Let's solve this one. It says consider this reaction between methane and steam. A flask of 2.50 decimeter cube was containing 4 mole methane and 5 mole steam. As the reaction began, the amount of CO was increased from 0.00 mole and became constant at 1.50 mole. Complete the table to show how much amount of reactants were used and the products were made. Now using this data, I know that in the beginning 4 mole of methane and 5 mole steam were there. Hydrogen and carbon monoxide were none in the container because they are the products. The question mentions that carbon monoxide is produced 1.50 mole. So 1.50 mole were made. If you notice the ratio between carbon monoxide and hydrogen, you see it's a 1:3 ratio. Where 1.5 mole carbon monoxide was made, so 3 times hydrogen should also be made in the same reaction. So I will put that 4.50 mole hydrogen was made in the same reaction because it runs a 3:1 ratio. Between carbon monoxide and methane, the 1:1 ratio applies. So obviously, if 1.50 mole carbon monoxide is made, 1.50 mole methane was used up. Similarly, steam also has a similar ratio, so 1.50 mole steam was also used up, leaving behind 3.50 mole steam. So the leftover amounts are 2.5 methane, 3.5 steam in the container, while 4.5 hydrogen is made and 1.5 carbon monoxide is made. The Kc expression will have hydrogen with a cube and all other substances without any exponential powers except for one. So when we put the values from the equilibrium concentration table, we should not forget the fact that the volume is 2.50 decimeter cube, so each value would be divided by 2.50 because concentration means moles divided by volume. That's why I'm putting each amount and I'm dividing it by 2.50, which was the volume. In this case, the reactants are denominator like every time and the products are the numerator. We can cancel out the carbon monoxide values and other values to make our calculations simpler. Using a calculator, because my mental math often sucks, the Kc value in my case turns out to be 2.49. Now we can also talk about the units because in the numerator I have hydrogen with a cube, so mole per decimeter cube with a cube. Carbon monoxide has simple mole per decimeter cube. Both the reactants in the denominator were simple mole per decimeter cube each, so I am writing mole per decimeter cube twice. When we cancel out all these similar units, we get to know that the unit for my Kc value in this case are going to be mole square per decimeter raised to the power 6. So we can also calculate units for various Kc expressions.